Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for Talented High School Kids. In this video, I want to talk to you about the Cauchy Completeness theorem, which tells you a very interesting feature of the real numbers and hence also of the complex numbers. And this feature involves the existence of limits. So before I go on and tell you about this Cauchy Completeness theorem, I want to pose a little question which will motivate why you might be interested in this notion of the existence of limits. So the question is simple enough. We just want to find root 7. And you may think, well, that's quite easy. I just put 7 and take the square root in my calculator and there's an answer. Of course, the answer that's given there is given in terms of decimals and it's just an approximation. So a question that's rather natural is, well, how did the calculator get that answer? And if you want a better answer than that, how do I get it? So perhaps a better way of rephrasing this question is, we have this abstract definition of what root 7 is. It's the real number which squares to 7. Okay, but if we want to get a feel for it, I guess we want to approximate it by, for example, rational numbers or decimal numbers. And how do we get increasingly better approximations? In other words, approximations which in the limit will give us root 7. So let me suggest to you the method that is from Newton-Raphson's method. Okay, what we'll do is we'll draw a graph of y equals x squared minus 7. So that's this parabola here. And what we're going to do, of course, is we want to basically look at the roots of this. So we want to see where this intersects the x-axis. So the way the method works is you find an approximation for the roots. So you think, well, 3 squared is equal to 9. That's pretty close to 7. 3 squared is bigger than 7, so it will be to the right of the correct answer of root 7. Okay, but at least it's close. So what we'll do is we'll take this approximate root, which we'll call x0 equal to 3, and we'll just see where it is on the graph. So let's look at the corresponding point above here. So the x value will be 3, and the y value will be given by x0 squared minus 7. So that's 3 squared minus 7, or 2. Okay, so it's up here. To get what we're going to do now is we're going to try to get a better approximate solution. So we're going to take the tangent line to this curve here, which approximates this curve close to here. And we're going to look, rather than at the intercept of this, that x-intercept of this graph, the x-intercept of this tangent line. Okay, so thinking of this tangent line as approximation to this thing here. Okay, and then this x-intercept here, which we'll call x1, will be a better approximation. And you can see it's a better approximation from the picture, okay? So by the shape of this graph, of course, it won't go, this new approximate solution won't be below root 7, okay? But it is certainly closer towards root 7. Okay, so let's find out the formula for this x1 here. Okay, so we need to compute this tangent line. So the first thing we need is the gradient. So we differentiate this to get dy dx is equal to 2x. That's the gradient there. So we want to look at the tangent line at this point. So the gradient at that point is 2 times x0. And so, of course, the equation of the line you can get from this difference quotient. So the general point of that tangent line xy is y minus the y coordinate here, which is x0 squared minus 7, divided by x minus the x value here, x0. That quotient here has to be the gradient of this tangent line, the derivative to x0. Okay. Now let's compute what has to be the x-intercept, the x-intercept x1 of this tangent line. So how do we do that? Of course, on this x-intercept, okay, y equals 0. So we set y equals 0 here. So in this equation here, the numerator gives us, well, I guess we negate this term, so you get 7 minus x0 squared, 7 minus x0 squared. The denominator, you get what? Well, the x-intercept we said was x1, so there's x1 minus x0 here, and that equals 2x0. And all we have to do is to solve now for x1. So we bring the denominator over to the right-hand side. So you'll get a 2x0 x1 term here. And then this minus x0 times this, you get a minus 2x0 squared on the right-hand side. So if you add that to the left-hand side, add 2x0 squared to this term here, you get plus x0 squared, and the 7 is there. So this equation can be written equivalently as 7 plus x0 squared equals 2x0 x1. And now you just need to divide by 2x0 to get your final answer. So x1, your improved approximate solution is x1 equals 7 plus x0 squared on 2x0. Okay, so that's one way to improve your approximate solution. And now what you're going to do is you're going to repeat this process. Okay, so you just basically look at the tangent line above this. You replace this parabola, you approximate it with the tangent line here. And then you look for the new x-intercept and you repeat this procedure. Okay. And so what you can do is you can use all the working out here, but you replace x0 with x1. And you can just keep repeating this procedure. And so what happens is that, well, if you're given the nth iteration, okay, as xn, that's the nth improvement for this approximate solution, that's your xn, then to get your next improvement, xn plus 1, you use this formula, it's 7 plus xn squared divided by 2xn. Okay? And so this is the Newton-Raphson method for finding approximate solutions, or rather improving an approximate solution to an equation. And the point here is that, well, of course, you would hope that as you keep repeating, okay, you get closer and closer to the final answer. And the scholium here is that, well, if we do actually know that the limit exists, okay, if the limit of these approximate solutions actually exists, then the limit L actually has to equal root 7, so it is the correct thing. So this is one of those cases where it's good to know that the limit exists. Okay, so let me show you why this scholium is true, and the answer is quite simple. Okay, so we're going to assume that this is true, and then we're going to look at this equation, which you can also think of as an equation of sequences. Okay, you can think of this as n goes from 0 up to infinity. Okay, and so this is also a sequence, and this is also a sequence on the right-hand side as well. So let's take the limit of both sides. So the limit as n goes to infinity of x to the n plus 1, that surely has to equal the limit as n goes to infinity of this right-hand side. Okay, so what's the limit on the right-hand side? The limit on the right-hand side is, well, so firstly, you know that xn, okay, it never goes below this root 7, so it never goes below this 0. So you're never dividing by 0. So you can actually just take the limit as n goes to infinity of the numerator divided by the limit as n goes to infinity on the denominator. And to work out this, you just basically substitute xn with the limit L. So on the right-hand side, you get 7 plus L squared on 2L. What about what's going on with the left-hand side as n goes off to infinity? Well, as n goes off to infinity, n plus 1 is also going off to infinity. So these xn's, okay, that's also, the xn plus 1 is also going towards the limit of the xn's, which is also L. And now what you can do is you can just solve for L. Okay, so this is equivalent to, you multiply both sides by 2L to get 2L squared equals 7 plus L squared. So that means L squared equals 7. And of course, that just means that L is equal to a square root of 7. And it turns out that, of course, from this picture here, you're not going to get a negative root here. So it has to be actually plus root 7. Okay, so that's a rather nice argument. And the key point, though, is, unfortunately, you can't just say the limit is equal to root 7 until you know that this limit exists. Okay, so that's a key point. And one way to guarantee that limit exists is something called the Cauchy Completeness theorem. So this isn't something that I'm going to prove, and partly because the proof depends on how you define the real numbers. Okay, and in fact, in some ways, you can define it to be a feature of the real numbers. So sometimes there's no proof. Sometimes you define the real numbers in such a way that you don't actually need to prove it. Okay, but this is a feature. And to try to motivate what happens in this Cauchy Completeness theorem, perhaps one way is to argue as follows. So suppose you have a sequence, A0, A1, and so forth, and these can be complex numbers or real numbers. Okay, that's the situation in which Cauchy's completeness theorem works. Okay, so you have something like this, A0, A1, A2. So you imagine, and suppose it actually heads towards some sort of a limit like L like this. So okay, so we're going to start in the case that we know that the limit exists. So what does it mean for the limit to exist? So that means that eventually, if you think of this as being sort of like a discrete time system, so you're moving in discrete time, and this A is moving in time, right? Eventually, you can get as close to L and stay as close to L as you like. So if you wait long enough, these sequence values are such that they can get as close to L as you like. They all stay as close to L as you like. And what that also means is that if they're all close to L as you like, that means they're all close to each other as you like. Okay? And what Cauchy completeness theorem says is the converse of this result. Okay? The converse of this result. So that if eventually all these sequence values get as close to each other as you like and stay as close to each other as you like, then the limit will actually exist. Okay, so that's the Cauchy completeness theorem. So let's state it formally and properly now. Okay, so firstly, as usual, we need to have a level of closeness. Okay, so that's given by some epsilon, which is some positive real number, epsilon. Okay, and the next thing is you're saying that if you, given this level of closeness, there's a time, a waiting time, that if you wait after that time, okay, something happens. Okay, so that's going to be some waiting time m of epsilon. We can make it to be a real number or an integer, it really doesn't matter. So you want to say that after this point in time, so if you're looking at sequence values a and am, where say n is greater than m, and you're looking after this time, so they're both greater than m, okay, something happens. The differences between the values of an and am is less than epsilon. So suppose that happens. So suppose that for any level of closeness epsilon that you like, okay, there is a wait time m epsilon such that after that time, if you take any two elements of the sequence after that time, the distance between them is less than that level of closeness epsilon. Suppose that happens. So that's called the Cauchy criterion. Cauchy criterion for epsilon and the Cauchy criterion in general. So if that happens, then this limit exists. So it's an existence result about limits. Okay, so it's a little bit complicated, and I think the best thing is probably to see an example where it works. And in particular, I want to show you this corollary, which follows from the Cauchy completeness theorem. And in this corollary, it is something that actually applies in this situation here. Okay, so let's see what's going on here. Okay, so the corollary says the following. Suppose now you have a sequence of real numbers, and it's actually decreasing. So what you have here, you can see from the shape of this graph that when you draw this tangent line, okay, and if you're on the right of this root 7, you draw this tangent line, okay, the tangent line is always going to point like this, so that means that your next approximation is always going to move towards the left. Okay, so you have a decreasing sequence here. Suppose you have a decreasing sequence, and suppose this is bounded below by some real number b. So bounded below means that all the elements in the sequence, all the numbers in the sequence, are at least as big as b. Okay, so suppose that happens here. So in this case, just from the shape of the graph, you know that you never go below this root 7, and in particular, you'll never go below 0, for example. Okay, this is never going to happen. Okay. So this is bounded below, and so we can apply this corollary in this situation here. In this case, the limit exists. Okay, so if you have a decreasing sequence of real numbers which is bounded below, okay, there must be at some limit to that. Okay, it has to have some limit to that. And pictorially, when you try to envision this, this is something that hopefully you see is something that you want to be true. Okay, so what we'll do is we're going to prove this using the Cauchy completeness theorem. So how do we do that? So we'll use a type of argument which is argument by contradiction. Okay, we're going to suppose that this is false. Okay, well, if that's false, it must be that this Cauchy criterion cannot hold true. If this were true, then the theorem says that this limit exists. So it must be the case that this is false. For it to be false, remember this criterion is about finding this m epsilon with this property for every positive epsilon. So there must be some epsilon, some level of closeness for which this is false. So what we're going to do is we're going to suppose that this Cauchy criterion fails for some epsilon greater than 0. And what we're going to do is we're going to look at this sequence of numbers, this decreasing sequence of numbers, and I'm going to pick a subsequence of that. So we're going to pick certain values, okay? And how am I going to pick certain real numbers from this sequence? So it's called a subsequence, okay? So the first one we'll pick is, we'll start with A0, okay? And we're going to keep picking some of the numbers from this sequence. And so suppose the ith one here, capital AI, is equal to the nth sequence in the original one. And then we're going to use the fact that this Cauchy criterion fails for this epsilon. So it's not true that you can find an m epsilon for which this is true. Okay, so in particular, when you've reached this level, okay, this am, even when you've gone that far out, it's not true that you can always make sure that the rest of the sequence, the distance between elements between them is less than epsilon. So that means, so basically remember we're saying that this fails. So you can't guarantee this, which means that you can go far enough out and find another sequence element for which this is false. So what we do is we're going to go further out, we're going to pick m greater than n. Okay, so we're going to go further down the sequence from an to am, such that the distance between an and am is at least epsilon. And we're going to call this the next element in my new subsequence, capital AI. So capital AI plus 1 is going to be this am. And it's going to be the one, remember there's a decreasing sequence, so it's going to decrease from an, okay, from the previous element here by at least epsilon. And now we can keep going. So this is an inductive definition. So we keep finding elements in the sequence, which are later on, where each time you're decreasing by at least epsilon. So that's my sequence A0, A1, A2, and so forth. At each step, you're decreasing by at least epsilon. And of course, if you keep going, so these are just elements inside my original sequence, you can go below any real number that you like. So you can eventually go below B, and that value is one of the values of the original sequence. And that contradicts the fact that this sequence was bounded below by B. And that's how you prove that, in this case here, this has a limit. And this is a proof using the Cauchy Completeness theorem. So there are other ways to prove this result. Sometimes people take this as a key feature of the real numbers, and then they try to prove the Cauchy Completeness theorem from there, but I've reversed the order in this particular example here. So I hope now you can also use the Cauchy Completeness theorem to prove existence of limits.